హలో
సార్
యా యా యా
ప్రెజెంటేషన్ది కూడా స్క్రీన్ ఓపెన్ చేసుకొని రెడీగా ఉండండి సార్.
అదే చేస్తాను. ఒక్క నిమిషం.
ఒకసారి ప్రెజెంటేషన్ స్క్రీన్ పడితే వి విల్ చెక్ ఇట్ సార్.
అవునా?
ప్రెజెంటేషన్ స్క్రీన్
అదే షేర్ చేస్తాను. ఒక్క నిమిషం. చిన్న కరెక్షన్ అయిపోయింది. ఓకే almost done. Okay, so ఇక్కడ స్క్రీన్ షేర్ కదా.
క్లిక్ ఆన్ ప్రెజెంట్ నౌ సార్. ప్రెజెంట్
ఓకే. Full screen complete. Now that this has to be
ఫుల్ స్క్రీన్ సార్.
కనిపిస్తుందా?
విజిబుల్ సార్, విజిబుల్.
ఓకే shall I start?
ఇంట్రడక్టరీ స్టార్ట్ చేస్తున్నాను సార్. సార్
ఓకే,
థ్యాంక్ యూ సార్. Go live. YouTube. So good morning all of you. I K. Srinivas, convener of this web series on advances in mechanical engineering conducted by Department of Mechanical Engineering, DVR and Dr. H.S. MIC College of Technology, Andhra Pradesh, India. Welcome you all, and my warm welcome to our Honorable Chairman Dr. M.V. Ramanarao Garu, Vice Chairman Sri N. Srinivasarao Garu, Director M. Srinivasarao Garu, and CEO Sri D. Pandurangarao Garu, and our Principal Dr. Y. Sudhir Babu Garu for this webinar series. I also welcome all the HODs. Our college, DVR and Dr. H.S. MIC College of Technology, was established in year 2002. So it is accredited with NAC with A grade, and departments are accredited with NBA also. Now it is an autonomous institute. In our college, our department is one of the largest department accredited with NBA. We regularly conduct faculty development programs, workshops for the benefit of faculty as well as students. We hope you all enjoying this particular webinar series. Now today I take privilege to introduce our honorable resource person Dr. Pattabhi Ramaiah Garu for his valuable session on micromechanics of polymer nano-composites. Dr. Pattabhi Ramaiah B. joined School of Mechanical Sciences at IIT Bhubaneswar as an assistant professor in 2017. Prior to this, he held postdoctoral research fellowship positions in the IMT School of Advanced Studies, Lucca, Italy. He worked on photovoltaic solar cells with Professor Paghi and Masdar Institute of Science and Technology at Abu Dhabi, UAE. He worked on polymer nano-composites and biometric structures with Dr. Kumar Garu. He received his PhD degree from Bauhaus University, Weimar, Germany, under the supervision of Professor Rob Juk, where his PhD topic was adaptive multi-scale methods for fracture. He has developed several novel multi-scale methods by combining various continuum-based computational methods like VAC, DRKPM, solid shell, and XFEM with subscale models such as atomistic and phase field methods. He is an editorial member and reviewer of several international journals. His research interests are adaptive multi-scale methods for fracture, failure mechanics of hierarchical structures, fiber reinforced and nano-composites, photovoltaic solar cells, and lithium-ion batteries. He teaches fracture mechanics, vibrations, and theory of machines courses at IIT Bhubaneswar. We are very happy to welcome Dr. Pattabhi Ramaiah garu for this session. Thank you, sir.
Yes, thank you thanks to the HOD, K. Srinivas garu. Shall I start?
Yes, sir.
Yeah, good morning all of you. Yeah, thanks for the nice introduction. Actually, the title says that mechanics of polymer nanocomposites. Actually, I will be talking about micromechanics. So this is because of the dimensions of the materials that we are dealing with. So they will be of the order of micro scales. That's why they are known as the micromechanics. Okay. So without much delay, let's get into the business straight away. Probably you'll be wondering why these load transfer mechanics are required to be studied. So the genesis is like this. So therefore the title says like evaluation of interface. So if you look at the fiber nanocomposites, so usually the fibers are embedded in the matrix. And then because these two materials are two different materials, matrix will be epoxy and fiber will be something like glass fiber or carbon fiber. So two different materials embedded in the matrix, combined together. So therefore, naturally, there will be some chemical reactions between these two materials when they are joined together. So therefore, the first line says that the chemical and physical interactions between the fiber and matrix during the processing of composites. So that's the main region which leads to the formation of a thin interface or interlayer. Okay, so this interface is quite crucial because this is what this is where the load transfer happens. Okay, so therefore, studying the interface is quite important. So you can have a look at the picture. So you can see the fibers, the micro scales. So they look like this. Probably it can be a glass fiber or carbon fiber. So you can see a cortex direction, so which is along the vertical direction. And then the matrix is somewhere here, little on the other side. So in between the fiber and matrix. So this interface material is naturally developed because of the chemical reactions. Okay, so this is the point to be remembered. So I'll have more evidence with SEM images and all. I'm going to show them in the coming up slides. Okay. So therefore, the fiber matrix interface includes the two-dimensional region of contact between fiber and matrix. So that's the important part. So the interface region actually interfaces or joins the fiber and matrix smoothly. Okay. And if I look at the properties of the interface, they are not constant. Okay. So it's a region of some finite thickness. Yes. If you have any questions in the middle, please feel free. It's not visible, sir. It's not visible?
Sir, the voice is not audible.
The voice is not audible. Yes.
Voice is clear and the screen is also clear for us.
Okay.
I request all the audience to pin the screen which is having the presentation and then unmute yourself. Dear members, please go through the screen of presentation and just click on pin. Then you can see the screen. If it is still a problem, please switch on to YouTube live streaming also. Thank you. Sir, please continue.
Okay. So I think the voice is clear now and we can be able to see the slide as well. Anyway, yeah, thank you. So therefore, this thin region of some finite thickness extending from a point in the matrix where the local properties start to differ from the bulk properties to the original fiber surface. In other words, interface ranges it spans some thickness, and one side of the interface the properties are going to be matrix properties, and the other side it's going to be fiber properties. The fiber and matrix properties are entirely different. So if you look at the modulus, so that will be of the order of 10 to the power of 3, something like that. because matrix is a very soft material, whereas fiber is a very hard material. So therefore, there's a difference of maybe 1000 in modulus. All right. So therefore, the interface properties smoothly varies from fiber properties to matrix properties. And you'll be wondering, because if you look at the thickness of the interface, it will be much smaller compared to the dimensions of the fiber as well as the matrix. Okay, but this small region governs the mechanics of flow transfer. So this region is the region which is main important for the quite important for the transfer of load transfer. Okay, so therefore, engineering this interface is quite important. All right. So I took all these images from the paper that I mentioned at the bottom of the slide, Wu et al. Okay. So if you want, you can have a look at the article for further details. I'm going to cover as many details as we require. All right. So therefore, in this paper, the authors have considered, so commercially available carbon fiber T300. It's a reinforced in epoxy matrix, and the fiber diameter is of the order of 7 micrometers. It's actually 7 micrometers, and tensile modulus 230 GPa, and density is 1.76 grams per centimeter cube. Whereas the epoxy is high temperature curing epoxy matrix 5228. It's cold with a tensile modulus of 3.5 GPa. You see, it's of the order of almost like 100. It's not 10 to the power of 2. It's not 10 to the power of 3, but there are some materials. It can range up to 10 to the power of 3 as well. And the density is also much lower compared to the fiber. It's 1.26 grams per centimeter cube. So these are the materials the authors have considered to analyze and investigate the presence of the interface in such composite structures. So what they did is they took the fibers, several fibers, and then embedded in the matrix, and the picture on the right top indicates the cross-section image highlighting uniform distribution of carbon fibers in the matrix. Okay, they actually prepared a fiber matrix composite, so just like any other composite, and then they cut the cross-section, and then you can look the cross-section as something like this. Okay, so the important feature of this is more or less every fiber has got similar environment. Okay, so therefore, so that's the beauty of this. So in other words, we don't need to model we don't need to simulate the entire material. We can take one fiber and its surrounding matrix and study their properties, like the load transfer mechanics across that fiber, and then extend such mechanics to other fibers as well. Okay? So therefore, that's how the mechanics are studied. That part I'm going to cover in the coming parts. Okay? And they prepared this composite as mentioned over here. So rise the temperature from 25 to 130 degrees centigrade, hold there for 1 hour, and subject to a pressure of 0.6 megapascals at 115 degrees centigrade. Right? And again rise the temperature from 130 to 180 and hold there for 2 hours at 0.6 megapascals. And then increase the temperature to 190, hold there for 3 hours without pressure, and the heating rate that they considered is 2 degrees centigrade per minute. Okay, that's how they prepared the composite. All right, so let's see the results. These are the important parts. Okay, so again, I would like to reiterate these words because they are quite important. So the chemical and physical interactions between the fiber and matrix during the process of composites leads to the formation of a thin interface or interlay. If you look at the picture A on the right top, so you can see the fiber cortex and interface and matrix towards the bottom. All right. Note the resolution of this image is 200 nanometers, so that is 0.2 micrometers. Okay, so that's why it is known as the micromechanics. All right, so that's the fiber bulk. It continues there, so it's a part of the fiber that is shown in the light. And then you see, consider the part of the fiber looks so big, and then again this is part of the matrix. So it's a very tiny region. Interface is a very tiny region. Okay, it's definite over here. Like the thickness of the interface ranges to the size of the lettering's interface. That's it. That's the size of the interface. Okay. So the enlarged image of carbon fiber portraits with inset somewhere here, like the enlarged image of the carbon fiber is shown in figure B. You can see the scale is 10 nanometers. All right. So again, these words are mentioned over here. The boundary between matrix and interface is wave-like. It's a wave-like. So because it is naturally formed, all right, and no clear boundary can be observed between the fiber and cortex, the fiber cortex and interface. This is again, it is naturally formed, so we cannot expect a uniform sized or shaped interface between fiber and matrix, particularly at the subscales. Subscales, I mean micro and scales below that. Okay, so the properties of interface are different from the properties of fiber and matrix, so that's as expected. So the properties will vary from fiber to matrix, right, in the interface. Okay, so having said that, so here is another image, scale of 20 nanometers, where you can clearly see the interface highlighted. Okay, so the size of the interface is of the order of few nanometers. So the entire scale is 20 nanometers, and the interface ranges almost like 1/4 of that, maybe 5 to 6 nanometers, or close to 10 nanometers, 50%. And part of the fiber is shown over there, and part of the matrix is also shown over there. Okay. And you can see the gray scaling. So on one side of the interface, you have dark material, and on the other side, that is towards matrix side, the material is light. So which indicates that, you know, the properties are also different from fiber to matrix. Okay, so this small region, remember, that decides the behavior of the fiber matrix composites. All right. So therefore, the bottom line is a thin and amorphous region is recognized at matrix. That is light gray, clearly exactly matching the property of the matrix. Okay. So exactly towards the end of the interface, the properties are matching with the properties of the matrix. Okay. But at this scales, you can see the wave-like structure, and then there is no uniform shape or size for the interface. All right. I hope you're able to follow. So let's extend these studies to some of our practical cases. For instance, if I consider unidirectional fibers being laid in the matrix, so the interlayer plays a key role in smooth stress transfer between the matrix and fiber. All right. So when I apply the load, unidirectional load as shown in the first picture, then the interlayer is going to play a role in smooth stress transfer between the matrix and fiber. The interfacial strength between the fiber and matrix significantly influences the load carrying capacity of the composite system. So, okay. So therefore, the interface properties decides the load carrying capacity and hence the failure of the composite system. All right. So that's why that is quite crucial. Several studies are dedicated to engineer the interlayer stiffness and strength of multi-material systems. Obviously, in other words, if I can engineer or tailor the properties of the interface according to my requirements, then obviously I can enhance the strength of the composite system. So therefore, that's how many people find opportunities, and as a result, you can see a lot of literature on this grading or tailoring the interface properties according to requirements. We're going to see how the stress is varying across the interface, and then how we can tailor, how we can reduce the stresses. All those details I'm going to discuss very soon. By the way, so this is how the failure can happen. So if I consider fibers being laid in matrix and then subjected to external loads, so the failures could be like, it could be a pull-out where the fiber breaks into two and then the fiber pulls out of the matrix. That's one of the failure. And then you can see kind of bridging and fiber rupture, and of course matrix rupture, debonding. So debonding is nothing but no perfect bonding between the fiber and matrix. Okay, so these are some of the types of failures that are possible, and all this happens because of the properties of the interface. Okay, so therefore studying the interface properties is quite important. And again, so I'm going to, as I mentioned, you see, this is the author's, this is the authors have considered such type of composite system, where you can see, I don't know why the mouse is not working. Anyways, so look at the second row, first picture. So this picture we have already seen, and then we understood that, you know, every fiber has got similar atmosphere. So therefore, if we can study the properties of a single fiber, as shown in the second row right picture, so the fiber being pulled out or subjected to external load. So obviously, in the fiber matrix system, so fiber is the loaded member, because matrix is soft, so it elongates, so it cannot take the load, but rather it transfers the load. So therefore, the load will be taken by the fiber. So therefore, the interface between the fiber and matrix helps to transfer the load from the fiber to the matrix through shear. Okay, so that's why the shear stress between the fiber and matrix, which is known as interlaminar shear stress, ILSS, popularly known as, so that decides the load carrying capacity of the fiber matrix system. Because based on the ILSS, if the external load or external stress is more than the ILSS, then obviously there will be some debonding or breakage, depending on the boundary conditions and other properties. All right, so that's the essence of this picture. And so as I was mentioning, so the fiber can break. So therefore, some failures, some types of failures are listed on the rightmost picture. So you can see the matrix, fiber, and then fiber breakage, interfacial debonding, and then in the middle picture you can see the matrix crack. So the crack is being generated in the matrix and it is propagating. So that is also possible because of the fiber breakage. So the matrix can crack, and yeah, so this can further enhance depending on the external loads with continued external loads. All right. So 9 is one of those first researchers who examined the suitability of shear lag approach for stress transfer in composites. He has proposed some crucial or important papers. You can see two of his papers are listed at the bottom of the slide on the use of planar shear lag methods for stress transfer analysis of multi-layer composites, and generalized shear lag analysis, including perfect interfaces. So these two, there are many papers, and these two are quite important. So he's the one who proposed the shear lag theory, based on facial interlaminar shear stress. And if somebody is interested, so this is quite popular theory. So you can refer to 9's papers, and then the main assumption. So this is what is important to me. The shear lag analysis is the state of the plane strain relating the radial and shear stresses in equilibrium equations. Okay, so the main assumption is the plane strain. So therefore, it applies to large thickness bodies. Okay, so this is applicable. In other words, the plane strain theory has been applied in the shear stresses while developing the equilibrium equations. Okay, I'm going to give you a mathematical model. So this is what we developed. Just give me a second. Just want to have a one. All right. So just like 9's shear lag theory, so what we have done is, so from now onwards, the results or the methodologies are adapted from this paper. This paper is not yet published. So stress transfer through gradient interfaces in people's composites, as mentioned towards the bottom of the slide. So I am also involved there. So my name is there at the very end. So I am also involved in developing the theory of this three-phase, so-called three-phase system. All right. So as I have shown in the beginning, so we understood that, you know, there is a very thin interface that is being generated because of the chemical reactions between the fiber and matrix. So that's what exactly we want to simulate. So the picture on the right in the slide, it shows three different phases. Three different phases. It's a composite system. So the first one is fiber, and in between matrix and fiber is thin interface layer has been modeled. Okay, and we want to study the mechanics of this composite system when the fiber is subjected to external load, provided the matrix is fixed to the bottom, or an equal and opposite reaction will be created at the matrix bottom surfaces. In other words, I applied a sigma naught load vertical direction onto the fiber, as you can see, and my coordinate system goes down because I want to study the as a result of this external load, how the stresses are being transferred fiber and across the interface and hence the matrix. Okay, so that's why I selected the coordinate system towards the downwards, that is Z, and the radial direction is mentioned over there, R, and the radius of fiber, interface and matrix are given by V, C, D respectively shown there. L indicates the length of the system that we consider. So if I apply the equal and opposite forces, you can identify that the reaction forces on the matrix will be rho sigma naught, where rho is b squared by d squared minus c squared. This is not very difficult. You can easily apply derive this, because you apply the force balance like sigma naught into area, that must be equal to the force that is to be balanced by the matrix. Okay, so therefore you can easily establish the relation. All right, so this is the kind of system that we considered for the analysis, and fiber dimensions are, the origin is at the center, so the radius is from 0 to b, and interface is the radius of the interface ranges from b to c, and the matrix it ranges from c to d. Okay, that's the geometry of the system. So the conditions are mentioned over here. The top end of the fiber is subjected to a tension of sigma naught. So it's nothing but the stress of the pressure of sigma naught is being applied on the top surface of the fiber. The bonds between the fiber interface and interface matrix are assumed to be perfect. So this is also again one important assumption. So we assume a perfect bonds between fiber and interface and interface and matrix. So the elastic modulus of the graded interface varies as a function of the radial coordinate. In other words, we are varying the modulus or grading the interface across the radial direction along the r direction. So that is the important part. We are not grading the modulus along the axial direction, but in the radial direction. The reasons are, you can see by looking at the results. And fiber debonding is not considered. Okay? The frictional forces between the fiber and phase are neglected. So usually one can consider the fiber debonding as well. All right. Something wrong? Okay, so the fiber so everything is fine, right?
Yes.
Okay, so the fiber transfers the load to the matrix through the interface. So that is what we understood. So now the point is how the load transfer happens. So that's what we need to investigate. For that, so what we did is we considered the equilibrium equations along the axial and radial directions. So in cylindrical coordinates, so these equations are the standard equations as I mentioned over here. And if I can solve these equations, then I can estimate the stresses along the three directions, like along r and theta direction, r, theta and z direction. Then the shear stresses and the rz, tau rz. So because the other components will be zero because of our assumptions. So because we assume the plane stress theory, plane strain theory. All right. So the stress components are estimated through a generic stress function. Okay. So in order to solve these equations, because there are four components to be solved: sigma r, sigma theta, sigma z, as well as tau rz. So two equations which are difficult. So therefore, the standard solution for this kind of a problem is to solve these equations using a stress function. Okay. The stress function is something like Fi of r, Gi of z plus Hi of z. Okay. This I indicates the phase in which we are applying this stress function. For instance, if I can be 1, 2, 3, where 1 can indicate fiber, 2 can indicate the phase, and 3 can indicate matrix. Okay. All right. Yeah. So the phi should satisfy the equilibrium relations. That's the condition. So therefore, we come up with something like this. So these are the standard equations in any strength of materials approach. So if we select a phi function like this and apply the equilibrium relations, then we can estimate sigma z, sigma r, and tau r z in terms of f, in terms of phi, the stress function, like this. Okay? In other words, if we can estimate phi, automatically the stress components can be estimated. Okay? So therefore, this phi function or estimating the phi function for the given problem is the main challenge. So if I look at the literature, around 1960s, the main job of the researchers was to develop the appropriate stress functions for a given problem. For this particular problem, that is the three-phase system, this phi function is going to work, considering the loading and boundary conditions. So this phi function is going to work. Okay. So there is extensive mathematical analysis further on several papers. So believe me, so you can adopt this phi function, and the task is to estimate Fg and H based on the loading and boundary conditions. Once you know phi, then you can estimate the stress components using the equations mentioned at the very end. All right, this is how we approached, and then a detailed list of boundary conditions are mentioned over in this table. All right. So for instance, I will read out some conditions. The others can be easily further extended. For instance, the first condition is the axial stress at r is equal to 0, r comma 0. So that is z is equal to 0. Must be equal to sigma naught. So that is the applied load. And then sigma z in the interface, that 2 indicates the interface at z is equal to 0, and at any given r it must be 0. So in other words, the interface doesn't take any axial load. So the load transfer in the interface happens through shear arm. That's why that is one of the conditions. And then the sigma z at r comma l, so that is at the bottom of the fiber, the axial stress is 0, because it's a free condition. So as the interface, so the interface at the bottom, the axial stress is 0, whereas the axial stress on the matrix at the bottom, so it is estimated based on the reaction forces, that is rho sigma naught, and the sigma z at z is equal to 0, sigma r at z, sigma z at z is equal to 0 in the matrix is 0, because this is the top surface and the free surface, so therefore it is 0. So like that, the rest of the boundary conditions are also estimated. So based on these boundary conditions, we can estimate the phi function as follows. Okay, so what we did is we adopted what is known as the energy function. So where we estimated the potential energy of the function. So in terms of a functional as shown over here. So potential energy is nothing but simply half integrated over the volume, stress times strain, so integrated over the volume. So we expanded this for each of the component, that is sigma z, sigma r, and sigma theta, and tau r z as well. So therefore the total potential of each of the constituents when estimated and accumulated, then that indicates the total energy of the system. And then we applied the Lagrange equations onto the energy functional. So the energy functional is mentioned over here, and so because everything is expressed, because the stress components are expressed in terms of the stress function, so therefore we consider the Lagrangian or Euler-Lagrange equations in terms of the stress function with respect to the stress function. Okay. So based on this condition, Lagrange's equation, so we get different sets of equations. When we solve these, then we are going to get the phi function. I'm not touching upon the mathematical details because that's a bit boring. So that's why I avoided detailed calculations. Like for instance, we have manually estimated the derivative, the Euler-Lagrange equations. That is the derivative of f with respect to phi prime and with respect to phi double prime, as well as with respect to phi, and then substituted them and got different sets of equations. Okay.
ನೋಡ್ತಾನೆ ತಕ್ಲಟ್ ಹೋಗ್ತದ ವಿಡಿಯೋ ಮೇಡಮ್
Video.
ಹೌದು
Mute. Please, I request members to mute your microphones.
Is that everything is okay?
Everything is okay.
ನಮ್ದು ಲಿಸ್ಟಲ್ಲಿ ಇದೆ ನೋಡು.
Sir.
Hello?
Sir, please continue, sir.
Okay. So that is the process. And now, as I was mentioning, so tailoring the interface or grading the interface to reduce the peaks of the facial shear stresses is the important thing that is to be done. So if I can reduce the stress peaks across the interface, then that means the composite can handle more stress or more loads. Okay? So therefore, in order to reduce the stress peaks, the modulus of the interface is graded along the radial direction according to different laws. When you look at the distribution of the stresses, then you will appreciate this. I'm going to show the distribution very soon, but before that I am explaining the grading mechanisms. So one of the grading mechanisms is according to the power law as well as the linear law. There's several types, so you can go for bilinear or whatever. So what I mean by grading is like this. As I mentioned, on one side we have the fiber, so the interface properties will be equal to the fiber properties on one edge as shown over here. Look at the picture on the right hand side. So it needs to be understood a bit. So if you look at figure B, you can see that green, red and blue, right? So the green region indicates part of the fiber, red region indicates the total interface, and the blue region indicates the part of the matrix. Okay? So without grading, the modulus of the interface is something like this, uniform color. That means the properties are uniform, just like the top picture, that is D. You can see the interface modulus EI being flat. Okay? So that is without grading. On the other hand, if the modulus of the interface is smoothly graded, as shown at the bottom of figure B, you can see the modulus is close to, it can be done in several steps as shown over here. So in one of the steps, the modulus is more or less equal to fiber and gradually changes to the matrix as we move towards the matrix in the radial direction. So this gradation can happen in several steps as mentioned over figure D. Okay, so that's how the modulus can be varied gradually. Okay, so this type of variation is known as the step variation. This is practical. I mean, this is adopted usually in practical experiments because these components are 3D printed. So in 3D printing, so the printing happens layer by layer. So therefore, a particular layer can be printed with a particular property, and then it can be the layer property can be smoothly varied. So that's how the interface can be developed. So it is based on 3D printing is based on additive manufacturing technology. So therefore, this grading is possible in 3D printing. All right. So according to power law, we can have something like P times R to the power of Q, where P and Q are the constants to be estimated, and these constants are estimated based on the continuity of the Young's modulus, because at R is equal to B, so that is at the end of fiber, we need to have the modulus of the interface equal to the modulus of the fiber, and similarly at R is equal to C, that is towards the beginning of the matrix, the modulus of the interface must be equal to the modulus of the matrix. So that's how the constants P and Q can be estimated. So if I substitute this, then I can actually get the variation of the modulus as power law. And similarly, I can estimate using a linear law. Okay? So this is not a linear law. So this is a whatever the one that I am showing in the picture. So that is actually step grading. Step grading, which is quite complicated to be computationally analyzed. Okay? So to ease the process, we are adopting either power law or linear law. So therefore, the constants P and Q or R and S can be estimated again based on the continuity of the Young's modulus. All right. So we are ready to discuss some results. For this purpose, what we did is we considered the following properties, like the ink smartness of the fiber is of the order of 230 GPa, interface is 117.5, and matrix is 5 GPa, and Poisson's ratio is 0.2, 0.35, 0.35 for fiber interface and matrix respectively, and radius of the fiber is 5, and interface is 6 microns, whereas matrix is 100 microns. You can see the thickness of the interface is just 1 micron. Okay, so so small is the dimension of the interface. So such a model has been considered, and because of the symmetry, I can apply the symmetry boundary conditions across the vertical axis. Therefore, you are seeing only half of the model. So the green one indicates the fiber, and the gray one indicates the interface, whereas the red part indicates the matrix. So a close-up of the this meshing or grading, the element sizes are shown in the consecutive pictures. So where the fiber interface and matrix are also marked, and you can see the overall picture of the three-phase system. So this is how we considered, and actually we estimated the results from our model, so that is analytical model, as well as the numerical analysis that is in this thing, Abacus. Okay, so we performed the analysis in Abacus also, and we compared the results. And these are the results of interfacial shear stress. Okay, so in the picture, it's quite interesting. So I'll try to explain. For instance, along the x-axis, what is mentioned over here is distance along the axial direction in micrometers. Remember, the 0 is at the center of the fiber. So if I go beyond 5 microns, then I'm going to touch the interface. Beyond 6 microns, I'm going to touch the matrix. Okay, so therefore, close to 6 or 7 microns is the important region. So that's why you can see a close-up of the graph from 0 to 10 microns is shown over there. So the important part is very close to the fiber and across the interface, the properties are sharply dropping. So that is the important part. Okay? So that's where the stress peaks are going to occur across the interface, and because of these peak stresses, it creates the interfacial debonding. All right. So that's why the region is very close to the fiber and within the interface region, and very close to matrix. Stress variation is shown over there. You can see a sharp drop. So let's say some 15 megapascals to maybe 1 megapascal within a distance of 4 microns. Okay, such a sharp variation of the properties are happening, and these graphs are mentioned over there. Like ungraded analytical indicates the blue line, ungraded in FEM indicates the blue dotted, and linear graded analytical indicates the orange line. Linear graded FEM is indicated by the pink line. So the properties are not exactly matching, but the trend is similarly shown there. There are many reasons for not exactly matching properties, but what we are interested in is whether the trend is similarly observed in both FEM as well as analytical models. Analytical models are perfect. So you can see from ungraded, the blue line, and linearly graded, the peak stress drops from 15 megapascals to 10 megapascals. Okay, so that's the importance of grading. Whereas on the other hand, if I go for power grading, so the stresses further drops to almost like 5 megapascals. So the stresses drops by 1/3, which is quite significant drop in stresses. So these drop in peak stresses decides the load carrying capacity of the composite system. All right, and this interfacial shear stress is the very key component. So therefore, the bottom line is by appropriately grading the material modulus of the interface, then we can reduce the peak stresses. And similarly, the radial stresses are plotted over here. Again, the similar trend, like the peaks are dropping within a small distance from, let's say, 25 megapascals to more or less like less than 1 megapascal within a distance of 2 micrometers. Okay, so that's the important part. So we considered a domain of almost like 500 micrometers, whereas all the mechanics are happening within 2 micrometers, 2 microns. So that's why the title should be like micromechanics. Okay. And again, see, the drop is exponential, and we can observe similar trend. Ungraded, the blue line, and the orange line linearly graded, and then the green line power gradient. So you can see more or less like 20, 15, and something like close to 11 or 12. Okay, the peak stresses. So that's how it began, and then it is dropping to more or less close to maybe 2 megapascals within a distance of 2 microns. Okay. So again, the grading plays an important role even in the radial stresses as well. Although the drop is not that significant, but interfacial shear stresses, it is quite significant, and that's the main purpose. The interfacial shear stresses decides the debonding. All right. So again, the axial stress, obviously the axial stress, we can't see any distinction or influence of grading, because they'll be happening across the axial direction, and yeah, we don't expect, because the grading is along the radial direction. So therefore, the influence of grading cannot be seen along the axial direction. So as a result, you can see all the stresses are the distribution of stresses more or less they overlap. Okay, so therefore, it's not of much importance. All right, so there is an explanation for the power grading, because we see significant drop in properties with respect to power grading. So we try to analyze the reasons, and we understand the distribution of the modulus in case of power law as well as linear law shown over here. The fourth picture, so the power law is green line, or linear law is the orange line. Okay. So we see a sharp drop of properties within a small distance using power law. Okay. So therefore, this is helpful, because we need to have less modulus in order to reduce the peaks, because that creates the space for more elongation, and hence the stresses will not peak up. Okay. So therefore, in case of power law, so the influence is quite significant. So that's the bottom line. And so this plot is interesting. So this plot is along the radial direction, whereas the previous plots they are axial direction. Okay, axial direction means the z direction along the length of the fibers. So along the length of the fibers, how the shear stress is varying. Okay, within sharp distances, it is picking up and dropping down. Whereas along the radial direction, so from 0 to let's say 15 micrometers, because the dimension of the matrix is the radius of matrix is 100 microns. So we stop down at 15 microns, because beyond that, more or less the properties are uniform. By then already the properties of the this thing, let's say axial stress, they are saturated in matrix. So therefore 15 microns is good enough. So 0 to 5, it indicates the fiber. 5 to 6 indicates the interface, and then beyond 6, it's matrix. So you see the properties are sharply dropping. First of all, from within 5 to 6, the properties are varying. Like on one side you have a large stress, and on the other side you have a very small stress. Let's say it is dropping from 50 to more or less like close to 0. Okay, so because this is how the interface properties are changing across the interface. So that's the, as we were mentioning, like because the properties or the load transfer mechanics will be happening in the interface, that is clearly shown over there. By the way, the picture on the top indicates the axial stress, and obviously axial stress, it should drop like it should be maximum around the fiber surface and minimum at the matrix surface. So the trend is exactly as predicted. And in radial stress, obviously we should expect, because the grading is happening along the radial direction, so therefore the influence of grading must be seen over there. Whereas in case of axial, no, we don't see, because the grading is along the radial direction. As a result, you see the ungraded to graded. So again, the power law plays a significant role. Have a look at the this thing, the zoom picture. So you can clearly see, the power law is quite helpful in dropping the peak stresses significantly as compared to the linear. Okay. So this is the distribution of the radial stresses, and the distribution of the shear stresses again is shown over here. And again, you can see the power law is playing a role there. So therefore, in all the cases, the power law grading is quite useful. That's the bottom line. That's the analysis that we performed, and we are about to publish this part. And meanwhile, what we did is we analyzed the different shaped fibers, the curved fiber, and the results like the radial stress, axial stress, and other types of stresses are also analyzed. And then if the authors are interested, if any of the readers are interested, listeners are interested, they can refer to this paper. And the mechanics of the curved fiber, basically the stress transfer mechanics across the interface. When the fiber is curved in nature, then you can see such results in this paper. I'm not going to go through such details because those mathematical details are a bit complicated. All right, so instead what I would like to touch upon is another interesting natural mechanism, so that is known as the nacre. So nacre is again a natural structure, and the mechanics of such natural nacre happens at the micro levels. So therefore, micromechanics of engineered interfaces in nacre-like composite structures is also an interesting phenomenon which can be extended to several things. So therefore, we studied that as well, and then I would like to touch upon that over here. And so before going further, so probably let's understand what is nacre. So nacre is also known as, exists in several types of structures. For instance, red abalone, say seashell. So if I go to, any beach and sea or river, and I can naturally see such type of shell type of structures lying on the shore. Okay, and if I capture one of the wet shell and try to break it, it's quite difficult to break it. On the other hand, a dry one, I can easily make it into powder. Okay, so one of the seashell structure is shown over there, and then if I look at a microstructure of the seashell, it is like it's coated with calcite layer and nacreous layer, and several types of growth lines are also there. Okay, so a close look at a particular point is shown over there, where we can observe a hard material, so made up of calcium carbonate, and a soft material. So in other words, it's like a brick and mortar type of structure, where the bricks are made up of calcium carbonate and the mortar is actually polysaccharide. It's a polymer. So if I look at again a close look at the structure at one of the points, the dimension or order of this picture is of about few microns, and then micrometers. So therefore, and another view is shown over there. So the tablet thickness is of the order of 5.5 microns, and it's like a brick mortar structure. So a 3D view of the brick mortar structure is shown over there, where the bricks are hexagonal in shape, and then in between the interfaces of the bricks, we have the polymer material. Okay, so it's 95% bricks and 5% polymer. Across the thickness direction, the brick thickness is of the order of 0.5 microns, whereas the interface thickness is of the order of 20 to 30 nanometers. That's the important point. Such a very small, thin layer of the polymer can enhance the strength of the wet shell to a significant extent. So I can say that the strength of such a structure is usually 3,000 times more than the dry shell. Okay. okay, or the calcium carbonate along. Of course, calcium carbonate is a very brittle material and it's difficult to break it its form, but when as a composite structure, when calcium carbonates are arranged in the form of bricks and mortar, so the strength of the assembly is 3,000 times more than the calcium carbonate. Okay, so that's the order of enhancement that we are going to get by going for a composite structure like kind of brick mortar structure. All right. So with this motivation, what we did is we considered this kind of a schematic. So you can see the bottommost picture, you can see a brick and mortar type, and similar picture is shown over there, brick and mortar type. And then these bricks are joined together, and at the joints we have the polymer. So the polymer is shown in the sub picture, and then a close view of the polymer is also shown over there. So you can see the dimensions are of the order of 20 nanometers. Anyways, the references for all these pictures are mentioned over there, and then it's a well studied phenomenon. And an SEM image of the fractured surface is also shown over there. So it's a brick and mortar type structure, and then we can see clearly the bricks and mortars being arranged in the form of brick mortar type structure. All right. So now we want to study the interfacial mechanics of this type of structures. So therefore, what we did is we printed such brick and mortar type structure. You can see a hard brick material, and they are connected by the interface, which is a very soft material. And such a assembly, when it is subjected to uniaxial stress, so what we observe is the tablets actually slide because of the presence of the soft matrix. So they actually slide a lot before the composite is actually failed. So you can see, because of the sliding, so there'll be crack initiations, many crack initiations, and then they continue to grow, and then they grow significantly until the material fades. So these pictures indicates the image is captured at different stages before the fade. Okay. Again, the relation or the common motivation is to study the stress transfer mechanisms and study the influence of the interface. In this case, the interface is created for our experiments. Of course, in structures like nacres, such interfaces naturally they exist, and in seashells, such interfaces have been developed over a few millions of years because of continuous interaction with the seawater. So seawater consists of several polymer based ingredients, and though they will be absorbed inside these small micro gaps, and then they form the polymer like material such that the wet shell will be really tough to fail. It has got significant toughness against the fail. All right. So since we want to study the influence of interface, again we studied that based on some computational studies, and we extended this for grading as well. So I actually adopted a similar model as Espinosa adopted in 2007 in his paper in 2007, extreme mechanics. No, I think engineering mechanics. Yes. All right. So such a model has been adopted, and then we considered a brick mortar type structure, and we performed a 2D analysis in order to investigate the influence of the matrix. And if I look at the 2D analysis, the layup of the bricks and the matrix, so they are like this as shown in this picture. And then, so a close look at arrangement of bricks and mortar indicates that they are repeating in nature. So therefore, what we did is we adopted an RVE, representative volume element, as shown over there. The RVE looks like this, and when it's touched, yeah, okay. So when such an RVE is repeated along the 2 dimensions, then we are going to get the full structure. Okay. So therefore we adopted the RVE with the dimensions that are mentioned over here. All dimensions are in micrometers. The tablet size is 8 microns, and the interface size is 0.025 microns, and the overall thickness of the assembly is 0.825 along the y direction. And you see that symmetry conditions are being applied in figure B, and we are holding on one of the tablets, and other tablet on top tablet is being subject to displacement. Under these conditions, how the stress is varying, so that's what we want to study. And a close-up of the discretization is shown over here in figure C. You can see, we have sufficiently meshed or discretized in such a way that we can capture the mechanics or the variation of the properties in the interface as well. And so the stress distribution, the stress distribution in the highlighted region is shown over there. And then you can see a kind of symmetry. So that symmetry can be seen over there. Like this is anyway for the entire tablet. So the stresses are peaking up at the edges. So that is the important message. So we considered the RVE. In the middle, they are the minimum, whereas very close to the edges. Edges means the vertical edges. So the stresses are peaking up. And since we considered 50% overlap, in other words, the size of the top tablets is equal to half the size of the bottom tablet, okay, more or less, because the interface thickness is quite small, 0.025 micron. So therefore, the stress distribution in each of the tablets is exactly symmetric. So I can see a symmetric behavior with the peaks being occur across the edges. Edges I mean left edge, middle edge, which is being separated by the interface, middle of the top tablets, and again right edge. Okay? So across the edges, the stresses are peaking, and in the middle they are quite flat. So therefore, if I can reduce the stresses across the edges, then the load carrying capacity of the composite significantly enhances. So that is exactly what we have done. So we created a very soft material across the edges, and then in the middle, so the material is quite hard, okay, because the stresses are very small there, and so you can see the variation of the coloring of the grading. So it's a very light gray color across the edges, indicating a soft material, and very dark color in the middle, indicating high modulus value. So as a result of that, you can see that the ungraded one is the peaks, stress peaks are in the ungraded are quite significant, and with grading, the stress peaks are slowly reducing. For instance, linear, parabolic, biquadratic. So in this case, the linear type of grading is working fine. Don't combine this with the three-phase system, because the mechanics geometry is entirely different there. All right. So therefore, in this case, the linear grading is working fine to reduce the stress peaks. The peak stresses plays a role over here. So therefore, the peak stresses must be reduced. So you can see like the peak stresses are reduced like almost like by 40%. So 1 to 0.6 by linearly grading. That is quite significant. Okay, so we extended this analogy for the, let's say, metal matrix composites. So we considered aluminum as the matrix, silicon carbide as the hard material. We also consider magnesium as the hard matrix and silicon carbide as the hard material. We consider different ratios, for instance 95 to 5, that is 95 silicon carbide, 5% aluminum, and similarly 95 magnesium and 5% silicon carbide. 95 silicon carbide, 5%. So like that we consider, and one of the cases, for instance, 6634, we could see some reduction in peak stresses, particularly for this magnesium system. Okay, so for this magnesium system, the peak stresses have been reduced from, let's say, closely to 66 or 67 to 45 or 46. That's a bit, yeah, you can see the zoom. So yeah, 46, yes, 66 to 46, almost like 20 megapascals. So therefore, the analogy is that we can definitely extend this analogy for even metal-metal composites as well. So in case of aluminum silicon carbide, the reduction is of the order of from more or less closely to 56 to again 46, 10 megapascals we have, so not bad. So therefore, the point is the method is working. So we can try such systems to reduce the stress peaks. So that completes my talk. I would like to thank UIC College of Technology for giving me this opportunity to talk about the micromechanics of stress transfer and School of Mechanical Sciences to perform all these computations. And I would also like to thank all the participants as well. Thanks a lot. There is some time for questions. Okay. I hope you enjoy the lecture. Let me know if you want to open the screen.
Yeah. Thank you, sir. Now
Yeah.
it is open for any questions from audience.
Okay, so there are
Audience,
no
any
further
questions, please?
Yes. Yeah. That means either you understood completely, you are satisfied. Yeah.
Sir,
Explain. Yes, please.
your mail screen is visible.
Okay, sorry. Okay, sorry. Okay, I think I need to keep it open.
In
Yeah.
YouTube, there are any questions, Rajesh?
Okay, I think there is somebody has
Sir,
written.
there are questions
Yeah.
from YouTube, sir. Rajesh is asking, please.
Yes. How to go to YouTube? Is there any limit? Or
That I will ask.
yes, yes, yes.
From Pamulan Manichandana is
Yes.
asking
Uh-huh.
how do you select the matrix and fiber material?
Okay.
Where material position is not exactly.
Okay.
One more question, sir.
Uh-huh.
Have you considered the porosity and what is the possible limit for it? This is the question from Deepak Shah.
Okay. What is the possible?
Have you considered the porosity?
Yeah, porosity. I got that
What
one.
is the possible limit?
Possible limit. Okay. Yeah. So probably in my simulations, I definitely don't consider. But in the practical cases, it is quite possible. I have shown the experiments by the authors where they have taken an image up to nanoscales. So perhaps we don't see any porosity over there. If at all there is porosity, it should be visible in the either the SEM image or the TEM image, because we have these images ranging up to nanoscales. Yeah, of course, these are quite possible. But the experiments are carefully captured because they are captured, they are performed in the vacuum. So therefore, probably the chances of generating such porosities are not there in those experiments. In practical, maybe it's possible. But in my computational model, I definitely don't consider the porosity. In practical, it is possible. And that can create other types of stress transfer. Either it can enhance or it can degrade. It can act like a crack initiator and then So therefore, the cracks can grow with the micro defects, micro or nano defects. They can act like a stress razors, and the cracks can initiate from there, and it can go up to the continent. So therefore, that is also quite possible. On the other hand, during the sliding, so these porosities may merge with the sliding tablets. So therefore, that sense they may help the stress redistribution of the stresses as well. That is also possible. Okay. So in my computational model, I definitely don't have such. Okay. And what is the other question? I think I answered that part. Did I miss any part?
No, sir, that is
Okay.
fine.
Okay.
And we have one more question from YouTube members.
Right.
They are asking that how to find Young's modulus and Poisson's ratio for a
Okay.
newly selected natural fiber.
Right. So usually the Young's modulus is estimated based on the load displacement curve. So fiber, as a single fiber, if you want, I don't know. But in my case, what we did is we performed the simulations. For instance, this maker structure, we performed nanoscale analysis or nanoscale, deformation mechanics also we studied. So in such case, we applied the load and then captured the load displacement diagram. And just like steel, the slope of the load displacement diagram gives us the modulus. Okay. So like that, we captured the modulus. So that's one standard way to capture the modulus. So the load displacement diagram is the key. And Poisson's ratio, probably I don't have any idea, because that depends on the reduction of area. So I don't know. For standard materials, Poisson's ratios are available in literature, or alternately we can also find, maybe in literature there are some techniques to find Poisson's ratios. Not aware. But modulus, yes, load displacement diagram. So that can certainly give the definition. Yes.
One more question. How to evaluate non-linear nature of stress strain behavior in composite?
Again, non-linear nature. You mean you want to estimate the stress versus strain, right? So again, load displacement and plot it. So naturally, it happens to be non-linear in composites, because it's not a linear material, and the properties are orthotropic in nature as well. So therefore, again, the answer is load displacement diagram. So capture the load displacement diagram, and it depends again on the analysis of this scale at which we are looking at. For instance, if I want to perform the micro or nanoscale analysis there, I can not apply in general some orthotropy. So therefore, I have to actually model the fibers and their orientation and the matrix as well. So that's what we are doing. And to this composite structure, we are applying the load and plotting the displacement diagram. So that's how we can estimate these. From there, we can estimate the stress strain as well. So that is possible. Because load by area gives me the stress, and then strain can be estimated based on the displacement. So anyway, we have the displacement information. So therefore, that's how we are doing. Okay. So in the bulk, so probably to take a practical specimen and then do computationally. Probably you can assume the orthotropic properties depending on the type of composite that you are considering, and subject that to load displacement to generate the load displacement diagram, and from there stress strain cost can be written. So that's one of the ways. Yes.
Sir,
Yes.
on behalf of all the participants and from DVR and Dr. HS MIC College of Technology, we are very thankful to you, sir, for sharing your expertise to all. So, and we are very thankful for immediate acceptance of our particular request to give this session. Thank you very much, sir. Thank you very much.
Yeah, thanks a lot again to the VR College, MIC College, for giving me this opportunity. And yeah, thanks a lot from my side as well.
Thank you very much, sir.
Yeah. Yeah, so that means that's all right. I can log off.
Yes, sir. Yes, sir.
Okay, thank you. Bye
Thank
bye.
you, sir.
Bye, sir. I request all the members to go through the feedback form which is present here in the chat box. Please fill the form. You will be getting the certificate immediately. And if you are unable to get the certificate immediately, please wait for some time. And while filling the form, please see that your email ID is correct. That is the only problem where you are not getting the certificate. Just please mention the email ID correctly without any spelling mistake. That is where you are not getting the certificate. That is the only reason. Here we will be checking the connection time to time. So there is no issue with the feedback form. We have rightly connected feedback form with the certificate. Please. Thank you all. Now we are cutting the call. Tomorrow we have session at 10 a.m. again. That is session 5 complete pattern. We will be addressing on fixed theory.